So welcome back, friends, to our last week of classes. This semester went fast and slow at the same time. It seemed like different points, but we are almost there, because for better or worse, the semester is going to be over soon, right? You just got to push through the last thing. Not unlike labor, actually, although I don't want to scare you. But let's see here. We are still talking about 3-level models for this week. We have a quiz to go over. We have a homework out. And I wanted to, again, remind you of the deal that I made. Right? Remember my deal for course evaluations? 12 out of 13 of you complete them. Everyone gets a point extra credit. That's my deal. And I'm giving you time in class. I have added my own questions to the course evaluations that are more specific in nature, so I'd like to get your feedback as much as you would be willing to give it. Good, bad, in between, all of it is useful in helping me plan what to do not only in this class, but in all my other classes as well. Let's see. Should we start? Are there any homework questions? Yet. And if not, that's okay, because you know what? This is due at the end of finals week. You got a week and a half. So you can just, put this off for now if you want. Like all of my homeworks, this one is based on a true story. All of my homeworks take place at Midwestern Red State University, because that pretty much covers everywhere I've ever worked. This one is based on my niece, Amelia, when she was little. She was a thumb sucker, and she wanted to have fingernail polish, and her mom would not let her until she stopped sucking her thumb as an incentive. Unfortunately, she never really did stop, and now she has a palate expander. So that's because if you suck your thumb, it messes up your face. So it's not good to suck your thumb, apparently. So, but the fingernail polish was more enticing to her than just the logic of being a big girl or a big boy, or the teeth thing. Yeah, the fingernail polish and being a big girl was a bigger sell than discussions about how she was ruining her teeth. She was not concerned about that at the age of 3 or 4. So my son still sucks his thumbs. We're waiting to see what's going to happen with that. Anywho, so no questions yet?
General, so I just...
Sure.
I don't know how to center language. I have no idea about that.
Sure you do. So the instructions, you have to center time and program, right?
Time in 0?
So time is 1 to...
9.
Yeah, and so how do you make it so that 0 is the new 1? Or 1 is the near 0, excuse me. Minus 1, that's it. Make a new variable, subtract 1 from the old one, and actually for program, which is coded 1 and 2, and it needs to be 0 and 1 instead, you can subtract 1 from that. Same thing. Just to give you, so there's, just like last time, there's 2 versions. There's a SAS version and a Stata version. In this one, the Stata version differs in a couple tiny ways because Stata blew up at me when I tried to run with 7 points of quadrature, and so I had to back it down to 5 to get the model to run. The other thing I wanted to point out is that for each assignment, I do the starter file for the syntax that has the names of the variables and stuff. This one, because we hadn't gone over a binomial model in class, I also gave you an example. Pull this up here. So this is what it looks like in Proclimics to do a binomial. A binomial just means that it's a percentage. It's the number of thumb-sucking instances out of total. So it's basically a rate. That's the outcome. So it's just like a binary outcome, which you guys did a homework on, in that it goes from 0 to 1, and the model predicts the probability of a 1. The only difference is that the outcome literally goes from 0 to 1, not just 0 or 1. So this setup right here is how you give it a percentage out of the original count out of total. And the only other difference is that the distribution is binomial. So that's what it looks like in SAS. So I gave this to you as a starter gift. So this is your model for the first section. This is your empty means random intercept model. If I go back to Stata, let me pull up question 7. The Stata syntax looks very similar we have the outcome after any logit, and then there is a binomial as an option that does the same thing. So this is your empty means random intercept model if you're using Stata. Otherwise, the code looks exactly like what you've been used to in terms of adding fixed and random effects. Fixed effects go after the DV, random effects go right here inside your bar statement. So let me know if you run into any problems. I'm happy to troubleshoot code. Like, you can just paste it into your email and be like, why isn't this working? I can probably tell you off the top of my head because I've screwed up every possible way that one can screw these things up. I have made the mistake before, I will guarantee it. Okay, so no questions yet? All right, should we talk quiz then? Your very last formative assessment. Congratulations. Yay. You did it. 14 points in the books if you did them all and did them in a timely fashion. So this was focusing on intra-class correlations in the context of 2 and 3 level models. So let's review. If I have a 2-level model, the intra-class correlation is the variance at level 2 divided by, of course it doesn't work, try it here. What? What goes on the bottom? Regular 2-level model. You've done these a million times. Level 2 and 1, so total, in other words, but I'm writing out the components. Cool. So that's a 2-level model. What if it's a 3-level model? Do it like this. I don't know why it like moves over. Come back to the left side. There you go. So this is 2-level. In a 2-level model, is there any other kind of ICC you'd have to worry about? In a 2-level model? No, that's it, right? I mean, you could get fancy and like switch it to put level 1 on top. That would just give you 1 minus the ICC, but that's really the only thing that you would have to worry about. In contrast, 3-level. There are several. So this quiz was designed to review a couple of them that are most useful in the context of clustered longitudinal data. So what do I need to change to make this, hey, come back. Come on. There we go. What do I need to change to make this a 3-level? If this is level 2 ICC is what I'm asked for. So what I want is the proportion of variance at 2 or higher. That's what that means. This one needs to grow, and so does the bottom. So these two are now analogous, because if I ignored level 3 and I just fit a 2-level model, the top one is what I'd have. Once I split out level 3, this is what it would look like. So the ICC at level 2 tells you the proportion of variance that's 2 or higher. In the context of a clustered longitudinal design, so time, person, group, it's the proportion of variance that's between persons or the proportion of variance that is cross-sectional. Now the other one that I'm asking about in your quiz is the ICC for level 3, which is the proportion of variance out of level 2 or higher that's actually 3. Let's scoot this over here. So that one, 3's on top. How do I fix the bottom? I got to take out this one. So here's the logic. ICC level 2 is splitting off 1 from anything else. ICC level 3 takes that anything else and splits it. So of the variation that is level 2 or higher, how much is actually level 3? That's the idea. What if I had a 4-level model? Could I do that? Sure I could. Am I going to make you guys do that in this class? No. But just for, as they say, shits and giggles, let's do that. Technical term. So we would have something like this, if it's 4 levels. You pick up level 4 down here. ICC level 3 would be that. Stop that word. It's like, no, I'm not going to let you teach today. Give up. And can you predict what ICC level 4 would look like? Any guesses? Yeah, isolate that one and get rid of that one, the level 2. Because the way these models work is that it's the variance at the low level, it splits into the high splits again, the high splits again. So this is testing the need for each successive level. Basically, is there anything that is above 1? Do I have clustering? The first one answers that. Okay. Of the level 2 variance, how much of it is level 3? Second one answers that. Of the level 3 variance, how much is level 4? That answers that. So each of these tests the necessity of the next highest level. And it would keep going if you had 5 levels. I've never tried a 5-level model. I have gotten 4 to work, though. It takes a long time to run, usually, especially if you have random slopes. So for that precursor, then, let's look at the story here. So we have a research project in which the effect of an intervention assigned to teachers on a student-level outcome. So we've got 500 students nested in 20 teachers. So this was a story from a couple weeks back. I'm extending the story to now say that we are measuring the students over time. Let's say that we live in a perfect world in which we have no missing data and they all got measured at the same 5 occasions. So if everybody is on the same measurement schedule with respect to time, what do I call that? Starts with a B. Balanced, yes. She wants to ensure that the teacher-administered intervention, so a level 3 intervention, in other words, is equally effective for students of different abilities. So this is what's known as a cluster randomized trial. When you have an intervention at the group level, power for that depends on the number of groups, sadly to say. But that's a whole separate question. So here's some questions about the design. So time is balanced. Everybody started at the same occasion. Everybody has 5 occasions, and they're the same 5 occasions. So based on that design, for time, what is the ICC for level 2? And what is the ICC for level 3? Those are my questions. What'd you put? Move this over here. So ICC level 2, in this context, of all the variation in this longitudinal outcome, how much of it is level 2 or higher? How much of it pertains to students and therefore teachers in time? Between students and between teachers is what I'm looking for. But I didn't give you any numbers by which to calculate this interclass correlation because I don't need to. If everybody has the same occasions and everybody started at the same time, what kind of variability does the time predictor have? It'd only be level 1, right? Because everybody's being treated the same with respect to time. So if a variable only has variance at level 1, what interclass correlation does it have? 0. 0. It's a purely within level variable. If everybody has the same occasions, there's no missing data, and everybody started at the same time, time is purely within persons. It has no between person variation. And this one, I would call it 0 as well, although technically it's undefined because the denominator would be 0. But there is no level 2 variation, which means there is no level 3 variation. So no ICCs whatsoever. So consequently, time is a purely level 1 predictor. We don't have to worry about smushing it, calculating the mean time for levels 2 or 3 or anything like that.
If
Yeah.
if this weren't the case, and we had to interpret it,
Uh-huh.
I don't want to say my answer because I think it's wrong, but how would we do that? So it would be the level 2 would be the portion, or the variance due to whatever the next level above level 2 is.
Mhm. So in this context, let's say that she has, she's doing this intervention across multiple grades, let's say. So we got like 3rd graders, 4th graders, 5th graders, and we're following them over time. If the intraclass correlation in that type of design is going to be something above 0, you would interpret that as the proportion of variance in time that is actually cross-sectional. If
I was
they,
looking at the notes, so what I wrote was this is going to be how much of the variance in student performance due to variation over time. What am I actually describing? Because it's not that.
it's variation that is not about time.
Oh, okay.
So it would be like how much of the data is actually longitudinal versus cross-sectional? Level 2 ICC gives you the proportion that is cross-sectional. That is person-specific, and if it's person-specific, that means it probably has teacher variance in it too. So that happens anytime people differ in time when they start the study, as well as potentially due to missing data or unbalanced time. The ICC for time will be something above 0, in which case you have to worry about it. Now, how to solve that problem is trickier because there's not one strategy that's universally the best one. Okay. So other questions on the first one? Okay, second one. Based on the design, what are the level 2 and level 3 interclass correlations for the variable of control versus treatment, which is teacher level, level 3? So teachers are assigned to a control group or a treatment group. That variable for control versus treatment, for control versus treatment, ICC for level 2, and ICC for level 3. What do you think?
Don't you have to know what level treatment versus control is to start with?
It's level 3.
Okay, that's what I thought.
So treatments are administered at the level of teacher. So some teachers are control teachers, some teachers are treatment teachers, which means that all their kids follow that grouping. Kids don't switch groups across time. Teachers are in one condition versus another. And, okay. It doesn't think I lost connection. So based on that design, how much of the variation in control versus treatment is level 2 or above? Don't think too hard. Your first instinct is probably correct. If control versus treatment is a level 3 variable,
Oh, it's just level 3.
it's level 3, so how much of its variance is 2 or higher?
All of it?
All of it, And all of it translated into a number is? So now, of the variance that's 2 or higher, how much of it is actually 3? All of it? Yeah. So a level...
Same definition for the first one, of the variance that's 2 or higher, what's 3, and then for 3, it's of the variance that's 2 or higher.
of the total variance, how much is 2 or higher? 1.
Oh, 2 or higher. Okay.
Yeah. Of the 2 or higher, how much is 3?
Okay.
So it's like a selectively partitioning the top. Yeah, like a wedding cake or something. Yeah. Yeah. Or a pyramid or, I don't know. Okay. So now here's some that involves actual math. So student ability is my covariate that was measured repeatedly over time. So do you think some students are more able than others? Safe bet. On certain occasions, do you feel more able than other occasions? Yeah, like last week of classes, not so much. Next week, gonna be much better, right? Or the week after that. So yeah, so this ability level variable, I have given you the proportions of variance at each level. So these are not interclass correlations, these are straight proportions. So, ability, the ICC at level 2, of the variance that's total, how much is 2 or higher?
So to calculate it, is it level 3 plus level 2 divided by the total?
Yep.
Okay, then it's 0.7 or 70%. Is that right?
So it is level 2 plus level 3 divided by the total.
But isn't the total just the sum of all of them, so it would equal 1?
The total is 1, yes. So it should be actually 90%, 0.9. So that the first ICC is splitting the 10% from anything else. So
I don't know where I got numbers. I was probably tired.
you might have done the next one. You may have given me the answer to the second one. But yeah, so if I have a variable that looks like this, that means 10% of it is level 1, which is time, 10% is longitudinal. That means 90% is cross-sectional. So given these results, most of the variability in ability is person or higher. So 90% cross-sectional, 10% longitudinal. Now, of that 90% that is cross-sectional, so those words right now give me my denominator. Of the 90% that is cross-sectional, how much of it is actually between teachers as opposed to between students? Yeah, so that it would be level 3 goes here. So yeah, 33%. I made the numbers work so that you didn't have to like get your calculators out, and I wouldn't be afraid to do math in front of you. I kind of am. Do you remember the Simpsons episode where Homer starts learning French and he forgets like English words because his brain is full? That's how I feel like sometimes. Like I can't do basic math because that stuff had to leave to make room for this. But yeah, of the variation that is level 2 or higher, of the variation that has to do with persons, of the variation that is cross-sectional, a third of that is due to teachers. So some classrooms have smarter kids in it than others. 33% of the variance in ability that has to do with person is actually doing with teacher. So if you see a result like this, that automatically means that you have to worry about the effect of that variable at all 3 levels. If it has variance at that level, it goes into the model as a predictor at that level. Last one. At what levels can each of the following predictors potentially have random slopes? Let me start with the easiest one. Level 3 control versus treatment. It can have a fixed effect at level 3. So there can be a mean difference between groups. But can it have a random effect? No. We would need a level 4. So predictors at the highest level of the model cannot have random effects. There's nothing for them to vary over. It would have to be that the difference between treatment versus control varied over site or school or some other level of nesting that we don't have in the story.
Is that why we don't have Christmas effects? I can't remember.
Mm-hmm. Same thing. Yeah, if it's level 3, it can only be at that level. So you don't have to worry about smushing it because smushing doesn't happen down. It only happens up. So yeah, let's do that too. So level 3, control versus treatment, fixed at level 3 only, no random slopes. There. Next one. Level 2, we'll call it student gender. Okay, I'm going to revise my question. At what levels do I need to worry about its fixed effects?
Isn't this what we did earlier? The 2 or above?
Yeah. Fixed at 2 for sure, right? Because that's the level it's measured. But we would have to know what the ICC level 3 is for gender. To what extent is there a gender imbalance across teachers? Because if there is one, meaning if there is variance at level 3, if the level 3 ICC is greater than 0, then we have to worry about a potential level 3 effect. And potentially level 3, if variance there. Now, at what level could we have a random effect of gender? Gender is level 2. So at what level could I have a random effect of gender? What do you think? Don't think too hard. 3. Higher. The difference between boys and girls could depend on who's teacher, right? Could vary by classroom. So because it's a level 2 predictor, level 2 student gender could have random effect at level 3. Last but not least, level 1 time varying ability. At what level do we have to worry about its fixed effects? All of them, right? Especially if we had a pattern for ability that looked like this one. All of them. So even though you're thinking about ability as something that varies over time, to the extent that students are more able than others on average, that creates level 2 variability, could have a level 2 effect. To the extent that some teachers have more able students than other teachers, that creates level 3 variability, which could have a level 3 effect. Fixed at all of them. And what if I don't put it in at all 3 levels? Then what have I done? Smushing, bad. And if someone looks at you and says, what the hell is smushing? You say, it's a conflated effect, man. And then they say, what the hell is that? What does that mean? What is the problem with smushing more formally?
It means you haven't fixed. So you're including variance at level 2 levels when you meant to only say 1. So you're attributing all the variance explained to within maybe what you actually have between variation too.
You are treating it as 1 variable, but it should be 2. So if ability has variance at level 2, it could have a different effect at level 2. If I only put it in the model at level 1, that assumes the level 2 effect is the same as the level 1 effect. And if I only put it in at level 1, but in reality, it looks like this, then I have smushed 3 different effects into one coefficient. And yes, have seen that in published papers. Mm-hmm. Yep, it's rampant. Now, random effects. At what levels could the effect of time-varying level 1 ability have a random effect? Can level 1 predictors have random effects at level 2? Sure. Could level 1 predictors have random effects at level 3? Yeah, both. Random at level 2 and or level 3. Yep. And that's where you can actually calculate an ICC for the random slope if it has both. If you have a random slope at level 3 and at level 2, you can calculate the proportion of slope variance that is 3 instead of 3 versus 2. 3 over. Same as the ICCs. And in the example that I have, we'll do that. Okay. Questions?
I think you've already accepted our feedback about video answers something.
Yeah, I'm recording. Got all the answers.
I like the way because I like you not only verbally give us the explanation but also typing. Thank you.
You're welcome.
But your evaluation is the longest one I've ever had.
My what?
When I finished my first page, I think it's over. But then I switched because there is most other evaluation we would have had just 1 page. That's all. And then I click on submission, but there's no submission. And then the next page. How do you feel?
You're welcome. By the way, I learned something useful from my earlier class. Apparently, since YouTube does its own closed captioning for my videos, which is sort of hilarious because it's guessing what I'm saying and it's not right a lot of the time. But apparently, you can search. Like if you want to hear me talking about level 3 ICC, you can put that in the search term, and based on the closed captioning, it will find where in the video I talk about that. I had no idea that had that technology, but yeah, that is cool. So yeah, you can just like you can search, your electronic slides for keywords. You can search keywords in that, and apparently it understands me when I say homework question. So you can search for that too. I don't remember where I stole that from. I think it was like an 80s movie or something. But I once had a professor that would stomp their feet when there was a homework question. Instead, they just go boom, boom. But like that doesn't like translate on video the same, so I have to do the fake cough. So anyway, yeah, I sort of make you guys work for it, don't I? That way when you get your A, you're going to feel really good about it. I don't just hand out A's. Right? I want a degenerate distribution, though. I want everyone to be in the A pile. That's what it's called, degenerate. Then it's just a constant, right? Anywho. Let's see. So we're done with that. We're done with that. Let's see. We were talking about random slopes, and I was attributing my understanding of them to Don Hedeker. Thank you, Don. He's at the University of Illinois, Chicago. Very famous statistician, an excellent teacher as well. And he drew a picture for me that allowed me to finally understand how you could have a random slope at level 2 and level 3 at the same time. So yes, by the way, when people come to visit, like job talks or they give talks, volunteer to be the person who like takes them to the airport, because then you get their undivided attention for like 45 minutes, and you can ask them questions that you otherwise wouldn't have a chance to talk to people. So that's my recommendation, because I got to do follow-up questions when I drove him back to the airport. Poor guy, I made him work for it. But hey, this is the picture that he drew me. So this is where we were left off last time. The idea, time within person within group. As one example of a 3-level model, it's a very common type of design, so I think it's useful to talk about that. If I have time, this is slide 14 in lecture 8. If I have time as a level 1 predictor, like in my quiz story where it's purely level 1. So everybody starts at the same time, so time is purely level 1. A random linear slope model could look like this. So we have at level 1 two placeholders for what the level 2 effects are going to become. So beta Oj is how each person gets their own intercept. Beta 1ij is how each person gets their own linear time slope. We come to level 2. Now we're going to define how each person gets those terms, and first off is a placeholder. So that's why these things are all in black, is because they're not parameters, they are placeholders. Delta Ooj is how each group gets its own intercept. Delta 1oj is how each group gets its own linear time slope. Those placeholders are then finally defined at level 3, where gamma is the term I'm using for fixed effects, 000 for the intercept, 100 for the random linear time slope, the fixed time slope, and then the random parts. So these V terms here, OOJ, 1OJ, that's how far off each group intercept is from the mean. This V1OJ is how far off each group slope is from the mean. So now each group has its own line, so to speak, right? Its own intercept and slope gives each group its own line. Now we come down here to level 2, and now it's time to talk about you relative to your group. So we pick up UOIJ and U1IJ, which is how far off you are from your group's intercept and slope. So these are group relative individual deviations. Your group is your anchor point. And now, once each person has their own line, beta O, beta 1, we come down here and we pick up E, which is the remaining distance of each occasion from the trajectory that was predicted for it. How far off your line you are at each occasion. So putting it together without the placeholders into one equation would look like this at the bottom here, Tij, time, individual, and group spelled wrong. The first term in parentheses is, all of that is the intercept. So gamma OOO is the mean of the group means, plus how far off your group is from that mean, plus how far off you are. And then the second bracket holds, parentheses rather, holds the linear time slope. The average group linear time slope is gamma 100. Then V is how far off your group's time slope is from that. And then U is how far off your slope is from your group one. And then E. So all in all, how many parameters do we have here? 2 fixed effects, right? Fixed intercept, fixed slope for time. We have at level 3, 2 random effects, an intercept and a time slope. Because those belong to the same group, we get a covariance at level 3. Group intercepts, group slopes correlate. Likewise, at level 2, person. Each person gets their own intercept and their own slope. They correlate at level 2. So it's like we have a block diagonal G matrix where there's a level 3 section and a level 2 section and zeros in the off places. So my chapter 11 that I put on your reading list literally has that for you. So I would recommend that. The first half of it is this type of clustered longitudinal design. And then we have E at level 1, which is, as always, uncorrelated with all the other levels. Okay. How are we doing? Yeah? Well, you're looking like, I'm not doing today. Now, are you wondering how these are not redundant? Because that was my question for a long time, is like, how can you have a random slope at both? And the key to understanding it is the deviation idea. So I have 2 different versions of a model to try and explain this here. This is the picture that Don Hedeker drew for me. I have somewhat of a photographic memory for certain things, and I can still picture it in my head. But let's say that we have a level 2 only slope versus a level 2 and 3 slope. So in blue, this is the 2-level version of it. So the black line here in the middle, that's going to be my average slope, like my gamma 100, excuse me. Let's say that I have 2 people from the same family. I have a mom and a dad. So relative to that slope, I can talk about how much steeper the slope is for dad versus mom. So the first one here, this slope is 3.5, this slope is 2.5. So relative to a slope of 2, dad's slope is 0.5 more positive. Mom's slope relative to the slope of 2 is 3.5, so that's 1.5 more positive. So it's these brackety things over here, the difference between the grand mean slope, the fixed slope, to get up to each person's. That's what level 2 random effects would give you. Now, random effects are supposed to be unrelated, like people are supposed to be independent. Well, if this is true, if both of these people from the same family both have positive slopes, then there's a commonality there, right? So instead of thinking of this as where's the person relative to the sample mean, it would look like this red family down here. So a 3-level split of the slopes would go like this. At level 3, we talk about the family mean slope, which is this red dashed line right here of 1, relative to the mean of the slopes, which is 2. So my family, on the whole, at level 3, has a slope that is less positive by 1. That's my VF right here. That's where the negative comes in. Now, relative to this family-specific red dashed line, where do the people fall? Relative to that, mom's slope is 0.5 more positive, dad's slope is 0.5 less positive. So it's not redundant, it's just a further partition. Rather than saying I'm starting from the mean slope and getting to each person, it goes mean slope to level 3, then level 2 relative to 3.
So Lisa, in
Yeah.
this class, all the triangles and dots are in the line, but actually it's like fluctuating around the line. So that's the difference from the individual lines, the arrow.
The E would be, yeah, how far off. So these are like predicted trajectories. The actual data points would be scattered around them, yes. And E would be the difference between the line and where you actually are.
And if I'm doing it in the generalized way, I cannot see that, right? I cannot see
Not exactly.
it. Okay.
Yeah, E is a concept in that the model's not perfect, but the E is not a parameter whose variance you have to estimate. It's non-constant, so it's this model, the default multi-level model framework, assumes that E variance is constant unless you put something in the model otherwise. But that's the default, is that the line fits equally well for all sorts of people. Like the E's are equally scattered around it. If that's not the case, then you would have to add something to the model that allows E variance to differ for certain kinds of people. Ironically, that's the field that Don Hedeker is probably most well known in. If you allow heterogeneity of variance as a function of person or predictors, those are called location scale mixed effects models. My first and only graduate student in quant psych at the University of Nebraska did his dissertation on those models. So I have some papers I can give you that we worked on if you're interested in those. But location scale mixed effect models is when you have different E variance as a function of predictors or randomly across people. So yet another topic I don't have time for. See, if they'd let me, I could do like 4 or 5 classes on multi-level models and not run out of stuff to talk about, I swear. Once you get into it, you just see how many things there are. But not today. So yeah. Question?
Maybe not a question, like I'm still very I'll say digesting, but just have a little bit difficulty to understand kind of intuitively because the slope moved first by depending on level 3, right? Because it's starting from V1.
Mm-hmm.
And then go back to V2, just I know it's just comment maybe, but just feel a little bit weird, Okay, we start from level 1 slope, and we took a level 3 first, then I could go back to level 2.
Mm-hmm.
This order is something I don't know, I feel a kind of difficult.
Why does it go backwards? Is that yeah?
I understand how it looks like,
Mm-hmm.
but yeah, super intuitively going back level 1 to level 3, then level 3 to level 2, just intuitively feel really. Sorry, I know it's a little bit difficult to
Yeah, it's.
comment, but
I think I see what you're saying, and I agree. It's a little bit weird, but it's like it comes down to this sort of idea. The fixed effects always go in at the highest level. Like they sort of trickle down eventually to multiply a level 1 variable, so it's still technically like level 1 effect. But like this is where it starts from. 3 is off from the fixed, which is the anchor. And then once you have that, then you get 2 is off from, and then you get 1 is off from. The other way to think about it is like, let's look at the blue lines again. If there is a commonality in how 2 people from the same group change, it would be more efficient to have them share a slope, because then you only need 1, and then see if that shared slope is enough, because then you could have a level 3 slope and not a level 2 slope. So like if mom and dad change the same, you make them share a slope, in which case you put a random slope at 3 but not 2. So in the same way that we talked about these sort of best and worst case ICCs, if people within a group are redundant, if they all change the same, then you give the group a slope. All the variances at 3. That's one extreme. The other is people from the same group have nothing in common when it comes to how they change. Then the slope goes at 2, not 3. Most of the time it's a little bit of both. People from the same group have some commonality in how they change, but they're not, it's not all or none. And so that's where segue, having a intraclass correlation for the slope specifically can help describe that. Of the slope variation, how much of it is because of the group you're in versus you as an individual? Likewise, of the intercept variation, how much of it is the group you're in versus you as an individual? The only thing you have to be careful about is when the model gets asymmetric across levels, you can't really do that. So for instance, if I had a quadratic effective time in the model, and I decided to put a random quadratic at level 2 in addition to random linear, but not at level 3. Let's say I added it, likelihood ratio test says you don't need it, okay. Then having a intraclass correlation for the linear slope in this setup wouldn't make a lot of sense, because what this linear slope means differs across levels because it's conditional at level 2 but not at level 3. Whenever you have a random quadratic effective time, the linear effective time, that random variance is instantaneous at time 0. Whereas down here at level 3 without the quadratic, it's just the linear variance all the time. So you'd be forming a ratio of like apples and oranges. It's still linear, but it's not the same linear, so it doesn't make as much sense. Okay, so we did talk about this today in the quiz. We did that one. We're not talking about smushing yet. I don't have the strength for that. Do you want to see an example?
Yeah.
Yeah, thank you, Molly. I'm going to miss your enthusiasm.
I'll be back next semester.
You're coming back, yeah. So funny story. Harry, is she here? No, Harry's not here. She usually sits over there. She's like, so is your generalized class about generalized? Because the description says it's longitudinal multi-level. And I was like, shit. Yeah, no, it just auto-populated my description from last year. So I had like 20 people signed up who thought they were going to learn longitudinal in the spring. Oops. So that was the cause of the email that I sent out to those of you who are registered saying, no, it's generalized. I had to write a new description. I got it fixed on Friday. The new description is up, and I think I've only lost one person that was like, yeah, that's not the class I thought I was taking. So even funnier was the advanced IRT class. The description for that is causal inference. Really. Because I read that and I'm like, nope, that's not advanced IRT, I'm quite certain. So those of you in that class just might want to check with Terry as to what exactly he wants to cover, because... Yeah, I should have thought of that. I missed it, so my bad. Yeah, apparently those descriptions for anything other than a special topics class are like etched in stone, and you have to like, you know, give blood in your first child to get them changed, from what I understand. So, anywho, let's look at an example. Example 8. Yeah, let's do that one. Here we go. Yeah. These are real data, actually. Old people data, as that was my first love in research, was cognitive aging. So these are a sample of same-sex twin pairs from Sweden. They were studying advanced aging. So they were all, it's 79 to 100 at wave 1, this sample. They were measured every 2 years for up to 5 occasions. So there, as you might imagine, there's quite a bit of attrition in this data set. They are same-sex twins, but they're either MZs or DZs, meaning they're fraternal versus identical. And so in my previous job, there was a bunch of people doing twin studies looking at genetics. Have you heard of those models? Heritability and environment and that stuff. Turns out those are just multi-level models too. Wait for it. The end of this is going to do a heritability analysis using proc mixed output. Drop the mic. So that's this. But it also works well just to show 3-level models in general. So the story is we're looking at a measure of crystallized intelligence information test that should not change over time except in presence of dementia or other sorts of decline. So this is something that's relatively stable across people. The first model is going to be a traditional 2-level model of time within person, ignoring the fact that these people are twins. So this is wrong, but it's a useful benchmark for pedagogical purposes. I hate it when it does that. Come on. Well, now Word is angry with me because it's like, I won't let you fix your typos while I'm here. There we go. There, now it's nice and aligned. So we have, we're back to general models again. So normally distributed residuals and all that. Because you could do logits and binomials with 3-level models, but that is another layer of complexity. So I have a couple things here with this data set. The way that the data came to me is with 2 ID variables. There was a pair ID that kept track of which family it was, and then within that family, it was twin ID was 1 or 2. So to create a unique identifier in SAS, I cheated. I didn't make a new variable. I said that subject is the unique combination of these 2. So it's not literal multiplicative, it's like combination. Stata would not let me trick it. So I made up a new variable called case that does the same thing. It's a unique identifier at the person level. So this is our 2-level model that's empty so that we can get a traditional intraclass correlation. In the SAS output, it tells you what the subjects is the highest level of the model, so it's number of unique individuals right now. Up to 4 occasions per person. I ended up dropping one of them because of attrition, just to simplify the analysis to some extent. So here are my variance components. So we have level 2 random intercept variance is the 136. Level 1 residual variance is back because this is a normally distributed residual situation here, so that's 23. I have level 2 over total is my intraclass correlation, which works out to be 0.85. So this is time within person, meaning we're trying to see how much of the variation in what is ostensibly a longitudinal outcome is actually cross-sectional, is actually due to person, and it's 85%. So that's really high. That's pretty typical in longitudinal data to see intraclass correlations that are much higher than in clustered data. So people are relatively consistent in their performance on this across time. 85% of the variance is because some people have more ability than others. 15% is due to within-person fluctuations in how they do. That 85% is greater than 0. There's my null model likelihood ratio test that SAS gives, and Stata gives this too as LR test versus regression, I think is what it's called. It gives you chi-bar in Stata, but not in SAS, for reasons that I'll never understand. And here's my fixed intercept, so on average, people get a score of 25 on this. Okay. So right now, if I tried to publish this, reviewer 3 is going to have a field day, right? You did a twin study and you're assuming people are independent? No. So yes, dear reviewer 3, you make a very good point. I appreciate your constructive feedback and attention to detail with respect to my sampling design. As suggested, I have now done a 3-level model. So here's my 3-level empty model. It's easy. One more random line in SAS. So I have pair ID as my level 3, and then the unique combination of pair by twin is my level 2. By putting them on separate random lines, I am ensuring that they do not have a covariance as intended. The analog in Stata is 2 sets of bars, that thing right there. Note that after each, I have this option covariance unstructured. That corresponds to the 2 type UNs on each random line in SAS. What that allows is a covariance between random effects at the same level. You always want that, and that is not a default in either program. One unique thing with Stata that I found out the hard way when I was working on the Stata code for my book. Stata assumes that any random effects after the first are nested. So even though twin ID is just 1, 2, 1, 2, 1, 2, because it follows pair ID, it understands that twin ID is nested in pair ID. Order matters. And that actually sucks when you get to crossed models in which you want to have 2 dimensions at the same level. It automatically thinks they're nested if you have more than one random effect. So that's where the extra layers of code to figure that out came in. Okay. So I did my little likelihood ratio test macro in Stata to compare the fit of this 3-level model to 2-level, and I did that in Stata via LR test. Okay. And here's what we get. Stata output looks very similar as usual. Now the subjects is the highest level of the model. So I have 351 twin pairs, and within a twin pair, I have up to 8 observations because I have up to 2 people and up to 4 occasions each. You can do the math to figure out that I don't have complete data with respect to twin pairs or with respect to time. So here are my variance components. Right now, these are orthogonal, which means I can sum them up to get my total. So 87 is level 3 variance across pairs. So some pairs do better on this test than other pairs. 49 is my level 2 person variance. So within a pair, some people are smarter than their twin. So twins are not identical replicates of each other. And then within a person, sometimes you score higher than others, and that's 23. That's level 1. If I do a likelihood ratio test to compare the -2 log likelihood difference between my 2-level model and my 3-level model, that output is right here. It is significant as you would expect. So yes, it matters that people are from twin pairs. They are not uncorrelated or independent. And here are my intra-class correlations. So my total, everything back together again, the 87 plus 49 plus 23, that is all the variability across time, people, and pairs in this outcome. That's 161 and some change. First thing I'm going to do is just do a straight proportion. These are not intra-class correlations. People label them that way incorrectly all the time. I get to be reviewer 3 in that case. It's not an ICC, it's a proportion. 54% is level 3, 31% is level 2, 15% is level 1. So the most influential here is family level differences. Some pairs did better than other pairs, and that is responsible for 54% of the information in this outcome. Me doing better than my twin is responsible for another 31%. That's me doing better than my twin on average. And then sometimes I do better than other times is 15%, level 1. So in your quiz, for a level 1 variable, I gave you proportions like this and asked you to do the ICC at level 2 and level 3. Here's this version. So ICC level 2, of the total variance across time, peoples, and pairs, how much of it is 2 or higher? How much of it is person or higher? How much of it is actually cross-sectional? 85%. Now, remember the ICC from the 2-level model? Going back a page, 85%. Huh. Coincidence? I think not. Correct. Now, in practice, in real data, it will wiggle a little, but it will basically be the same number because it's the same thing. How much is 2 or higher? If you don't put 3 in the model, 3 is embedded in 2 still. So 85% of the information in this outcome is 2 or higher. It has to do with people being smarter than other people, and people are nested in twin pairs, or it's cross-sectional, not longitudinal. So 15% longitudinal, 85% cross-sectional. That's what we got so far. The ICC level 3 then is of the variance that's cross-sectional. Of this 85%, of the variance that's 2 or higher, how much is actually at 3? It works out to be 64%. So 64% of the 85% is how you think about that. In other words, can we ignore the correlation of twins from the same pair? No. The correlation of twins from the same pair is 0.64. So this level 3 ICC is the effect size for whether or not we need a 3-level model. If we didn't, it would be 0. If people were independent, the ICC at level 3 would be 0. If people were robots who are exactly the same, the ICC at level 3 would be 1. Yeah. So in the words at the end of this, so you guys can hate me because of my long, torturous homeworks, but at the end of the day, you need to love me because of all these words I give you. Can I get an amen for the words? Amen. Correct. So all of what I just said is right here. So when I do these things, I usually start by giving them the percent at each level, because then they could calculate any intraclass correlation they wanted out of that. Fun fact, so Molly, you do genetics research? Or you have heard of it?
Oh, I adopted, so the
Oh.
whole Turner thing.
Okay. So here is the little secret that nobody wants you guys to know, because genetic analyses are like fancy and stuff. Do you know how you get a heritability coefficient for the proportion of variance that's due to genes and not environment and stuff? It is twice the difference in intraclass correlation between MZ and DZ twins. That's it. So there's a whole field of research that makes that way more complicated than it needs to be. But MZs and DZs, right? If you have an intraclass correlation, right? If MZs are more alike because they're genetically identical, right? Then they should have a higher intraclass correlation, right? And so the extent to which MZs differ from DZs and their interclass correlation is viewed as evidence for a genetic based relationship as opposed to common environment. So twice the difference in interclass correlation between MZs and DZs is your A or H coefficient, depending on what you have for heritability. And that means that it can go negative if the DZs actually have a higher interclass correlation, and it can go above 1 if the difference in interclass correlation is greater than 0.5. And those are footnotes on my latest publication that just got accepted. And by mine, I mean I'm like 17th author or something. So, but I did all the models, so there's that. So yeah. So now, same idea. We're going to try and fit a 3-level model for my level 1 predictor, which is actually H. In this design, the twins were 79 to 100 when they started, and they were followed for up to 6 years. That means time is going to have upper level variation. So I fit a 3-level model, and I got this. 0 at level 2. So the variability in age, 4 is at level 1 here, because occasions are different from each other. 8 is at level 3 based on how old they were when they started. 0 is at level 2. Surprising or no? Why is that not surprising? Because I agree. So do you think there's a relationship between being a twin and how old your twin is?
Yes.
By definition, they're the same age? So there's no within pair variance in age because they're twins? So this was sort of a duh, but to make the point, based on this information, I would do this for any level 1 predictor. That means that time, meaning age, needs to go in the model at 3 because some pairs started out earlier or older than other pairs. That is a cross-sectional age difference. It also needs to go into the model at level 1 because it's a longitudinal study and people are aging as they go through the study. It does not need to go into the model at level 2. And so that's coming next. In theory, we could have had level 2 variance in age if the twins were assessed at different points, because then they would be like older when they got measured, but they were very careful to work around that situation, measure them at the same time. So, all right, questions? All right, well then tune in for the exciting conclusion next time. So we'll call it a day. Office hours start now. Let me know if you need help with your homework. Otherwise, I'll see you Thursday. Right? Yeah, for the last class.
So this one will be related to our last assignment?
Uh,
I get started yet. So I just wondering if this one.
So this homework is a longitudinal 2-level model predicting a binomial outcome. I talked about it at the beginning of class.
So not about this one.
Nope. Nope, I don't give you homeworks unless I have at least a week after I cover something, and so I just decided not to have a 3-level homework. So, yeah, all right. So I will see you